So welcome to my talk, Introduction to Topic Modeling in Python. My name is Christine Doig. I gave a tutorial yesterday on machine learning. Just a brief introduction about me. I'm a data scientist at Continuum Analytics. We have a table out there, so if at any point you want to learn more about what we do, come talk to me. I'm originally from Barcelona, Spain, and I just moved to Austin over a year ago to start working at Continuum. And that's my Twitter account and my webpage with some of the talks I've given at SciPy, PyCon, EuroPython, PyTexas, etc. Just like a very brief introduction to Continuum Analytics. We offer a free Python distribution called Anaconda. If you were here yesterday in my tutorial, it was a recommended install. It makes it easy to install, especially packages that have C and Fortran bindings, things that you have issues installing with pip. It actually comes with an open source package manager called Conda that makes easy to build and install all kinds of packages. It's language agnostic, so you can build and install R packages, Java packages, MongoDB packages, etc. We at Continuum Analytics very firmly believe in open source, and we actually fund a lot of projects in the Python ecosystem like Conda, Blaze, Dask, Bokeh, Numba. We're also a very proud sponsor of this event, PyTexas, and also a bunch of Python conferences, PyData, SciPy, PyCon, EuroPython. And we are also hiring, so if you're interested, you can come talk to us later and also visit more of what we do as a company in our website. So about this talk, it's topic modeling in Python, and I pretty much try to have both a little bit of understanding the theory of what's topic modeling, and then also have a part that's like how do you apply topic modeling in Python, so that you can get, pretty much half of the talk is going to be on trying to understand the algorithms, and then the other half is like what libraries do we have available in Python to use to do topic modeling. And then I'm also going to talk about what other alternatives or other algorithms exist out there that you can also use, and then some additional resources. You can follow along these slides in this URL if you want to. So let's start with the first part of going through the theoretical background of what's topic modeling. And let's first introduce a little bit of what is topic modeling and where does it fit in the machine learning spectrum. If you were here yesterday, you're already familiar a little bit with this slide. Otherwise, let's kind of discuss how people classify machine learning application. And there's mainly two groups that people discuss, which is the unsupervised and supervised learning. And that is pretty much narrowed down whether your data sets contain labels or true values on each of the instances, or it doesn't. So in the case, if it does have a label, we're talking about things like supervised learning. And depending on whether that label is a categorical variable or quantitative, we're going to talk about classification versus regression. In the unsupervised learning is where you don't have that kind of label or true value. And so what you can do is just kind of cluster things together or try to find what's the structure or what latent variables exist in your data set. But you don't really have a way of predicting those new values in the way we use in like supervised learning. So I usually think supervised learning, pretty much your goal is usually to predict something. So you have a data set that's been built for you where you have this true label that we're talking about. And then you want to see like when new instances come, can you predict what the label or what that quantitative value is going to be for those new instances where you don't know that label. In the other side, in the unsupervised learning, you never have that label, so there's nothing really to predict. It's something just you pretty much want to explore things, explore how those instances fit together or how those variables relate to one another. So let's talk a little bit about why is topic model relevant. And I just happened to have, like, when I was preparing this slide deck that I gave for the first time at PyGotham, this year. It was August. Just the day before I was giving the talk, I found this article on the New York Times where they talk about their technology, and this article just came from how they move their recommendation engine to recommend people articles to read from collaborative filtering to collaborative topic modeling, and so it's a interesting topic, and it's being used in many applications. And here's an example of how in the New York Times are using topic modeling as one of their first steps into creating the recommendation engine to recommend users what articles to read. So I forgot to mention before, topic modeling is pretty much in this unsupervised learning category, and it's a way of thinking both clustering things together, but also trying to find what's the latent variables or structure of your data set. And we're going to look at it, some definitions that are there. You can find that one was taken from Wikipedia, another one from Princeton professor that's done a lot of research in topic modeling, and another one on MAL, which is a Java library for topic modeling. So these are I highlight some of the important words that are used in these definitions. So the first one is a topic model is a type of statistical model for discovering the abstract of topics that occur in a collection of documents. So you have a large collection of text documents, and you use these models to find what topics are in them. You don't know anything about them. Remember, we're doing unsupervised learning, so you don't really have a label. You don't have a category of, oh, this article is a sports article, or this article is about politics, or this article is about something else. We don't have that label. We just get a bunch of text, and we have to figure that out. Another article mentions more of this way of uncovering the hidden thematic structure, and then that's where we classify those type of algorithms between clustering, but also finding this structure between the variables, the data that you get. And these algorithms, as we've seen, can help us search, browse in different ways, collections of text documents, and bringing down really the cost of doing so, because in the unsupervised versus supervised learning, there's usually a high cost of figuring out or manually labeling those articles. So if you had to build an application that actually, someone had to label each of your text articles, whether they were from sports or politics or whatever topic that was, that's someone manually entering that information. Whereas in unsupervised learning, you just get a bunch of text, and the algorithm discovers it itself. And that's the last definition comes with this notion of it's a way of clustering words that frequently occur together in a way that we can define them as belonging to this abstract topic. So if we kind of get together these highlighted words, we can have an understanding of what are the characteristics of topic models. And we see this is exploratory versus predictive. It's on the exploratory side. We want to discover, we want to browse, we want to search large collections of unlabeled text data. We also care about what are the latent variables, what are these hidden thematic structures that are not labeled directly, but we can kind of extract from those algorithms. And there can be kind of abstract topics, maybe things that we don't really have a word of it, but it's a cluster of words that together have some kind of meaning. And we are doing a type of clustering. We're clustering words together, and we're clustering documents together. So when I mention clustering, in machine learning, there's a lot of different types of clustering. And I'm going to mention how this topic modeling clustering differs from other types of clustering that you might see in machine learning. So the first one is called hard clustering. And hard clustering is where each instance of your data set belongs to only one cluster. Can only belong to one cluster. So you have a hard separation, a hard division of lines that you set each instance and you classify each instance to just one of those clusters. We also have what's called hierarchical cluster, where you build this kind of hierarchy of of clusters, where you can have subclusters in your clusters, and kind of get this hierarchy of child and parent relationships. And then what's topic modeling is actually this third one, the soft fuzzy clustering, where each instance can belong to a certain degree to one of the clusters. And that certain degree can be thought of like a percentage of it, or a probability. So when I think about trying to understand understand this kind of machine learning algorithms, it's pretty useful to start with a black box, right? We're gonna put some pass some arguments if we're thinking about Python to this library, and we're gonna get some output. So we're gonna treat for now this algorithm that we're gonna call LDA or topic modeling as a black box, and try to figure out what's the input and what's the output of it. So as we said, the input is going to be this data set that's just going to be a collection of text documents. And as an output, we're going to get three things. We're going to get a cluster of words where each cluster is going to define a topic. And these words in this topic are going to have a certain frequency. It's important to note that in the topics, we see that one word can belong to several clusters. And we know that is from our English language, right? We have words that in different contexts can have different meanings. So that is represented in this type of modeling. Then different words in different topics can have also different distributions. And the distribution is what we see here as mentioned as frequency of words, right? Like in a certain topic, sports, you may see soccer a lot, in a very high probability, or ball, or things like that. And then other terms that might be less frequency, but they also occur in that type, within that frequency range. And then we have documents. And each of the documents, each of these text documents are going to have a distribution of topics. So they can have a combination of topics. It can be about politics and culture. It can have think about these abstract cultures. It can have like a different distribution of those topics within that document. And this is the distribution of topics that we see colored. So one of the one of the popular algorithms in topic modeling is called LDA. And LDA stands for Latent Dirichlet Allocation. And what is funny is in machine learning, there's two LDAs, one for supervised learning and one for unsupervised learning, that have nothing to do with each other, rather just like share the initials of the names. And so it's important to make sure we know when someone tells you I'm applying LDA to something, that they actually not just say LDA, but they say the full name, so that you're sure you know what they're meaning. Or if someone asks you, do you know about LDA, that you have the same context. So as we mentioned today, we're talking about the unsupervised learning, so the Latent Dirichlet Allocation. And then there's the other one called linear discriminant analysis, that's for supervised learning. It's important, I also wanted to mention that currently in scikit-learn 0.16, the LDA that they have implemented is this supervised learning. So not the one we're using right now. But I'm also going to give some information about scikit-learn, because they have an implementation of the Latent Dirichlet Allocation LDA that's going to be released in 0.17, which is the next release that's coming up soon. And there they've renamed the LDA that they used to have to the full name, so there's no confusion between the two of them. And we'll see some examples of that. So when you search for LDA in Wikipedia, you get this nice diagram. And the first time I thought, well, I'm going to add this diagram in my slide deck and try to explain it to people. And then when I started doing that, it started being really hard I don't know how many people find this diagram intuitive. Okay, can you come up and okay. I kind of tried to redraw this with like my notion of like boxes and input and outputs to make it a little bit clearer in my mind, and I think that ended up helping to explain that diagram to others. So going back to the diagram I had at the beginning, as we mentioned, we have m number of documents. Each of these documents are going to have n number of words, which we're gonna throw to this black box that we're gonna call LDA, and we're gonna output k number of topics that are gonna be just a cluster of words. In each of these topics, we're gonna have a psi distribution of the words in that topic. So word A in topic 1 is gonna have 0.7% of frequency. Then we're going to have this other phi, which is another probability distribution of topics per document. So let's say document A is going to have topic 1 0.1%, 0.2% of topic 2, etc. And then we have what's called these concentration parameters, alpha and beta, which is like if you have some domain knowledge, you know how your both your document topic distributions or topic word distributions are arranged. If you have some pre-knowledge, there's these two parameters that you can tweak to satisfy or to start to give some domain knowledge to your algorithm, and you give that through these two concentration parameters. So now if we go back to that diagram, we have that, we can hopefully understand it better and see where all those letters come from and where they fit in this diagram model. So now that we've seen the inputs and outputs, we can go and navigate into what's in that black box. And that LDA algorithm in that black box is an iterative algorithm where you start initializing some parameters. You assign randomly the topics and you initialize them, and then you iterate for each word in each document. You resample the topics for each word, and given all the words and their current topic assignments in the different documents. We're going to see each of these steps one by one so that we better understand them. Then you get the results, and then you evaluate your model. So let's first understand how we initialize the parameters. And pretty much the parameters that we need to initialize are these. We need to tell the algorithm how many topics we want to find. And that's kind of one of the limitations or drawbacks of the algorithm, is you have to have some preconceived notion of how many things you want to find. So that requires maybe either a little bit of domain expertise or testing different values for that parameter until you find a model that satisfies you. And then you also need to provide how many iterations you wanna get from performing the LDA, and that's something also you have to do and make sure that you are pretty much your model is converging to something. So you want to give a high number to assert that you're converging, but also each iteration is going to add cost to the computation of your algorithm. And usually you can also provide those alpha beta parameters, or otherwise you usually get some default values in the implementations. So once we have initialized those variables, then the algorithm is going to just do a random assignment of topics of each word in each document. It's going to assign it to a specific topic. And it's going to do that randomly. So this is a document, each of the dots is a word, and it's just going to color these words for a specific topic. So let's say we have 1, 2, 3, 4 topics, and we're going to say each of these words in this document and just randomly pick. And that's how you initialize the algorithm. And then it's going to iterate. So the K topics, we've already given the algorithm the K topics, and then based on those assignments we've already given it, it's going to be able to compute this frequency, both the frequency of words in each topic, and also the distribution of topics in each document. And so we're going to get this temporary phi and C and phi. And then we're going to resample for each word in each document and ask what should be the assigned topic for it, seeing all the other documents and all the other words in all the other documents and all the other topics. So pretty much asking these two questions. I'm not going to go in like the details, but which topics occur in this document? It's kind of a question that you can ask and say, and quantitatively measure that and say, oh, if let's say this one here, if it used to be green, but that's, green is not a topic that frequently occurs in this document, then it might count, we can quantify how much that is and what weight to give, whether that word would have that topic or not. And then the second question is, which topics like that word X? And based with these two questions, we can then make the assignment. And then you iterate over and over until you get to a convergence, and then get back the results with C and phi, then the definitive distribution distributions that are going to be outputted on your LDA model. So one of the hard things about unsupervised learning is that we don't have a training set that someone has prepared for us that we can then evaluate and have a truth set that we can compare and say, oh, we've done well, we've done bad. Because we don't have that label, we don't have that true value that was the first assumption in classifying into supervised and unsupervised learning. So because we don't have that label, how do I know how good my algorithm is? And that's important because we want to evaluate that. We want to compare across algorithms. We want to know how reliable it is. So there's, I would say, two different types of evaluation. One that's called human in the loop. So you build an application, or you bring someone to assess how good it is, or you can have some metrics that have been demonstrated to be able to assess how good your algorithm is. And the second one, of course, is less costly because always when you bring humans in your processes, that's gonna make it more costly to get a result. So in the human in the loop case, we have two methods. One is called word intrusion, and the other one's called topic intrusion. And I've also made graphics to demonstrate what that means. So in the word intrusion, what you do is swap one word in your cluster to another cluster, and then having humans in the loop ask them to find which one is the word that's an intruder to the topic. So if all those words are well related, so if a human can relate those words together and they're able to find the intruder, means that your topics have some cohesion together, that they actually belong together. If a person cannot find that word intrusion, probably means the words are just randomly assigned together, but they don't have any coherence. Then there's the topic intrusion, where you give people a document to read and the topics that were assigned to that document, and you intrude one topic that's not present there, and you ask them whether they can identify that topic. I've also mentioned that's very costly to have humans in the loop to evaluate that, and then you have to figure out what metric you're gonna correct answers, incorrect answers, what kind of metric you're gonna use to evaluate and compare models. And then there's the other thing that's called that we call metrics, and just coming out with ways of metrics that can allow us to assess how good document or our model can be. In one of them, it's called Cosine Similarity, and what it does, it computes two distances. One is called the intradistance, and the other one's called the interdistance. So, giving a distribution of topics per document, we split the document in two halves. And this assumes that the topics, so one of the big assumptions of this method is that assumes that the topics in the document are spread equal, like spread, that it's not like half of your documents talking about topic A and half of your document talks about topic B, because if that happens, this method does not work. It assumes it's mixed around the topic per se, like the document. So if we split it in half and we compute how similar is one half to its other half, and we come up with that value is similar, then it's that we compute that value for all our documents, and then we switch around the documents, the other halves, and compute that distance again to these two random assigned. And eventually, what you want to find is like the interdistance is high, and the intradistance, so between the sames, is so the distance is low in the half that belong together, and it's high in the one that don't belong together. And then you have a quantitative measure to compare different models and have like kind of a benchmark. So there's a ton of metrics that you can use, and I've added here some information on metrics that people usually use to evaluate their topic models. And you can read more about that in that resource. So now let's pretty much we're halfway. Let's talk about how we do topic modeling in Python. And the first thing is that there are that I know of 4 libraries that implement topic modeling, and the fourth one is coming soon. It's not there in like the stable release, but it's in the dev release. So we have gensim, we have GraphLab, we have a small LDA implementation, and then this scikit-learn Latent Dirichlet Allocation that's coming soon in 0.17. And just the warning of the current one is not it's referring to the supervised learning method and not the one we're talking about. That's why they're renaming everything. So let's take a look. I've prepared like a small example of each of those different Python libraries, and we can like take a look and relate them to the graph, the first diagram. Kind of keep that diagram in your head, so we know what arguments we can pass to the different implementations. So here I've added just like copied like the gensim example, and here we can see the LDA implementation of it. Here it's just like we're gonna see in the next step. Here we're just talking about the black box per se. In the next part, we're gonna talk about the full pipeline, and we're gonna see like where it goes to, what do we have to do to get into the phase of calling the LDA model. So in here, just think of it like we're loading our data set, our text document, we're loading a corpus, and now we're implementing LDA, which is the black box that we've been talking about. So we pass the corpus to it, what we're gonna call the dictionary, we're gonna call this, we're gonna talk about this in a second. And this parameter of like how many topics we wanna find. And the gensim LDA implementation, it has 2 modes. It has the online mode, so you can keep updating your models, and it has a batch mode. So in this one here, it's just using the batch mode with no online update, so that's why we update every 0. It just like updates all once. And this is the how many times, how many passes, how many iterations we're gonna do. So that's how you do it in gensim. GraphLab is has also an implementation of topic models, and they have their own data structure that's called S-array, and this one's just like how it's loading the documents, our collection of documents to cluster together. And we call topic model create. We pass these documents, and we assign the number of topics that we want to find. Again, how many iterations, and these alpha and beta hyperparameters that we saw that if you have any conceived notion of those distributions, you can tweak those parameters as well. In this other LDA implementation, again, it uses, this is like how you load the LDA data set here. And we first, it's a little different. We first call the class LDA, and then we fit to the documents. So we also can pass the number of documents, number of iterations, and then this random state, which can define like how you know, if you want to reproduce your result in another with the same data set, you might want to define the random state, so you always get the same results, and then you fit the model. This is new. This is 0.17 right now. If you download latest scikit-learn stable version, you're not going to get it, but it's going to be there, next release. So this is where you can find the latent Dirichlet allocation. It's in scikit-learn decomposition. And for now, I've removed how you get the data. We're going to see this in the pipeline section. And again, you can call, it's similar to the LDA API. So you first call latent Dirichlet allocation. You assign the number of topics, the iteration, and the state, and then you fit it. So as I mentioned, we're talking right now just about that black box, but we haven't really commented like if there's a particular way that we need to pass those documents into the black box. And here's where we're going to talk about that. So really, usually you cannot just pass like a bunch of text per se. There needs some pre-processing that needs to happen before you feed it to the model. In this case, we're going to talk about the pre-processing step and the vector space. In the pre-processing space, we're going to talk about tokenization, stop words. And then in the vector space, we're going to talk about the representation of bag of words and dictionaries. And then it's the phase of like model. That's the one we've just seen, like selecting the model, the LDA, or there's alternatives like NMF that we're also going to talk about. And then the last part would be the evaluation part. So when we talk about pre-processing in text processing, natural language processing, etc., there's a phase called how you tokenize your document. And there's different ways you can tokenize your document, meaning how you represent that document in a vector format. Like what are the features that you're going to consider in your document. And you can just consider each word as a token, like each individual word per se as a token of your document. But then that might not, we know in language that sometimes individual words don't have meaning per se, that sometimes they come together for a reason. There's n-grams, bigrams, and trigrams of words that pretty much belong together because they frequently occur and separately can mean different things. So I was doing this project on materials research science and how what were the different trends in different research papers of materials research sciences. And it using bigrams and trigrams, finding those can actually make a difference in how good your model is. Because, for example, if there's a specific method, you don't want to just have it, be method itself when you can want to distinguish between methods themselves, right? So in this case, we had or particles that have that have 2 or 3 words that go together that form the name of that particle or that component, whatever. So that really makes the difference. Other times you might want just to find entities, find nouns in your document. You don't care about verbs, or you might not care about adjectives, etc. And you just want to find those types of entities. You might want to have a combination. You might want to build your own tokenizer with your own rules. And then there's what's called lemmatization, which is just taking the lemma of your word. And it's important to understand your application because, for example, in chemistry or materials research science, lemmatization doesn't really make a lot of sense because the ending of a word is actually what's determining the component itself. So if we remove that, we're putting together a bunch of different materials or different chemistry components in the same bag. Whereas in like more general language text documents, maybe lemmatization does make sense in case, for example, of movie reviews or something like that, or news articles. What's also important in pre-processing is if you want, what words we're going to consider and whether we want to remove certain words, like words that occur very frequently or just language generic words, or also sometimes domain specific. So it's a word that you already know that's not going to bring any meaningful, or it's not going to be meaningful in your domain, then just remove it in your custom set of stop words. Then we need to represent those words in a vector space to pass the matrices to our computations. And that's where the concept of bag of words come, and how we represent a text document in a matrix format. So in this case, we can build a dictionary, which is going to have an ID and the word that ID represents, and then we can create for each of those different words or features, have some how we quantify, how we represent that word within each text document. And sometimes we might just want to count. Sometimes people just do presence or absence of the word. Other times we can do things like TF, IDF to balance for words that occur very frequently, etc. And so each of the lines in this example is a text document. And the first value indicates the ID of the word, and the second one, the count of that word in that document. Then we have the part of modeling. And modeling, we've seen mainly LDA, but then there's a bunch of others, and this is just like some. There's hierarchical Dirichlet process, random projections, and a bunch of others that gensim and other these libraries implement. And I wanted to go back to the scikit-learn example to see from beginning how does this pipeline look in that example. So we have this data set of the 20 news group. We have this, we import the latent Dirichlet allocation. We initialize some variables. We prepare the data set. And as I said before, we can either use just a term frequency, just count vectorizer, or we could use something different like a TF IDF. In this case, just using the count vectorizer. And then you can also set up when you're going to remove words based on maximum frequency, minimum frequency. If you want to have a specific number of maximal features that you want to find in your document, and if you do want to remove stop words or not. Then we can transform our data to this term frequency, and then we can start call our LDA and fit it to this representation of term frequency of words per document. The full example is available in this link, so you can also take a look at it. It's right here, and it has a little bit more. It also compares it with their other implementation, which is called negative matrix factorization. And one of the last parts of the evaluation I find also very useful when you're talking about large amounts of text, of not just for self, self-evaluation and also like sharing and seeing visual representation can be very helpful too. And then there's this nice package called LDA Viz that started as an R package, but now there's also Python LDA Viz, and it's a D3 visualization, and it wraps around so you can just like write it in Python. You get the JSON and everything that D3 needs to render it. And here's an example of movie reviews. I don't know if you can see it very well, but it's an interactive visualization where it groups each of these circles is a group, is a topic, and when I click to one, I get the top most relevant terms for that topic and their distribution. So I know now that 6 is about sci-fi, aliens, Mars, planet, space, Earth. And I can also see when I hover over one word, in what topics and in what frequency that word occurs in different topics. So I know that alien is in 6, 12, and 2, and I can come back and see, oh, well, this one's about Godzilla and apes, and there's also some, Jurassic. There might be also a little bit of aliens, but mostly the aliens are all in number 6. And so that way I can kind of explore what of these different topic, what's the topic of the different movies and how they group, and then like cluster them without anyone having to have labeled them priorly. So some other resources, I've added a bunch of resources that people can take a look at. There's a lot of more general of introduction papers, how to interpret the results, more of applications, and I really like if someone's really into the math and really wanted to understand what Dirichlet actually is and what LDA is. This one's a very good resource. It's a bunch of notebooks that you can actually run. And then this presentation here is mainly focusing around how you can visualize topic models. It also mentions the LDA Viz, but you also might find others. And then we have like 5-10 minutes of questions if people have any. So the question is, if you start with like spoken language, would you first translate it and then, would you first transcribe it and then fit it to the models? Yes. In this case, the LDA is pretty much working with text processing. So it is expecting tokens of words. There probably is other algorithms that can do more of like audio modeling, but I'm not aware of which ones would which ones that what libraries implement something like that. Yeah.
So you chose LDA from cluster, if I understand correctly.
For my cluster?
Yeah, LDA.
Yes, correct. Yeah, so we did try others, like there's LSI, or in some implementations called LSA. It's called semantic analysis. And that was like kind of like the first model that was used broadly. But that one has some issues with really finding topics that relate with one another, at least in our results. And there's also the negative matrix factorization that scikit-learn implements, and like here you can also have a full example of it. I'll have you implement it right here. And there's random projections in gensim in the slide here. There's the random projections, and then there's the hierarchical Dirichlet process. So there's a bunch of models that you can use to kind of cluster documents together, or more than clustering the documents together, you're clustering the topics that those documents talk about. So there's two different layers of it, right? And the good thing about not just using this soft clustering versus doing like more of the hard clustering of classifying each document to just one class is that usually text can be more complex than that, and you can have multi-topic documents, and being able to realize that that can exist and being able to correctly classify those might be very relevant for your application. Next. Yeah.
You talked about the evaluation, the human-based and the metric-based. How can you factor that back into your analysis?
So that's a good question. How can we factor that back into our analysis? In the case of human in the loop, you can at that point you might evaluate whether you might want to create some kind of semi-supervised learning method. So if you're already gonna, so my drawback against the human in the loop would be that if you're already paying someone, or you're already having a cost of someone evaluating your results beforehand, like after you've modeled, maybe it would also be worth it having them before you've modeled and have them kind of like label those documents in some other fashion, and getting us, some set of a data set that has some labels, and then use some kind of semi-supervised model to use that information inside your algorithm. Other than that, you could probably, other information that you could extract from the human in the loop is like what words they're not identifying correctly. So maybe you can identify a cluster that might not make much sense. And maybe then you can realize, oh, maybe it's like that cluster itself should be 2 clusters, and I need to like increase the number of topics to find. And then play with I think it's more of a comparison between your models to like maybe select which one you're happiest with, rather than saying how do I correct it. Any other questions? Yeah.
At a certain point, when you're getting inside the algorithm, do the alpha and beta have more meaning, or are they just parameters you tweak into the results?
So the question was if the alpha and beta have more meaning once you get deeper into the algorithm, or if it's just like a setting parameter. So they do have they can have an impact on if you have any but it's not very it can be rare, because really knowing how to set them in a way that match your preconceived notions can be a little hard. So usually people pretty much you leave them in like default, and you can tweak them a little bit and see like how that diverge in your end results, rather than trying to see. I guess if like you're really concerned with the mathematical assumptions that those parameters have, you can then like dig deeper. But otherwise, you're probably going to be more of a try error, try evaluate kind of approach. Yeah.
Certainly don't know the case with this topic modeling, but sklearn has grid search and randomized search specifically for hyperparameter optimization. So you don't have to do this. And you might think, unsupervised learning is not necessarily that easy, but it really is. You just create a pipe, overload a scoring method, and then retrain based on that. So you could use your cosine scores on a pipe.
Right.
To
Correct. Yeah. Okay, so it's already time, so thank you for your attention.